everyone, and welcome to Keysight Live from DesignCon. This is Carmina, I'm Marlo, and we're going to take you on an exclusive tour around our booth here at DesignCon in Santa Clara Convention Center. So over the next 30 minutes, we're actually going to walk you around our booth, and we're going to stop and talk to our solutions experts who are showcasing our latest solutions for design and test to accelerate your fastest digital designs. But before we get started, Carmina, is there anything you want to add?
Well, besides showing you the hits here, we're going to also want you to watch our live streaming of our Keysight Education Forum, which is tomorrow. You can register for them and then watch them on demand later. So we hope to see you there. So yeah, let's get started, Marlo.
Let's go.
Let's go.
So first up, we actually have a 224G transceiver test that's really accelerating advanced research for 1.6 terabyte research. And here we have John Calvin. He is part of the Standards Bodies Committees for OIF, CEI, and IEEE. And, you know, with this being one of our first shows that we've had live, how does it feel to be back?
Well, Marlo, it's great to be back here. We're seeing a lot of people, a lot of interest in the new products here, especially as the excitement builds around the next speed grade, which is 224 gig, which is what we're really talking about in this pedestal.
Great. Now, why don't you show us what you have here?
So, there's a lot going on at this station right here. We're basically showcasing two of our instruments. We have a real-time scope on the right-hand side, running at 112 gigabaud. That's 224 gigabits per second, and then we have the same signal coming into our DCA here over on the left. So these are two instruments that are sort of the cornerstone of our transmitter compliance and conformance efforts. When people try to verify that they're signaling to within spec limits, you need to choose one of these instruments here to serve your signal acquisition and your analysis needs. Up on the screen here, we have a list of the sort of jitter conformal measurements that get done. These are for the OIF CEI specification. And we have the exact same measurement set, but with some slight modifications for the IEEE conformance as well. There's 802.3 CK and OIF CEI 112 gig VSR, MR, LR. All these standards are supported with automated test tools. But a lot of people want to use the same instruments to do research for the next speed grade, and that's really what we're showcasing here. On top of the basic conformance test tools is the ability to do some of the analysis and jitter characterization that's necessary for 200 gigabits per second. Up on the screen here you see a 12-edge jitter decomposition. We're showcasing some of our special jitter decomposition that we have that now allows for separation of the level 1 and level 2 transitions, which has recently emerged in the recent spec revisions. Down here at in the center of this pedestal, we're driving all this with M8199A AWG. It's an arbitrary waveform generator. It's actually running two heads here, one to the right, which is running the real-time scope, and one to the left, which is synchronously driving the DCA. The DCA is actually receiving the signals through these 120 gigahertz remote heads they have. They're very handy and popular remote heads for these sorts of applications. It gets you the bandwidth and the noise fidelity you need, where you need it, close to your device under test. Really a revolutionary product here, and is doing a lot to serve the emerging market needs around 200 gigabits per second. This is really a key enabler. The real-time scope on the right-hand side, again, is also a key enabler. It's our air detector of choice. It's an instrument that we'll be using going forward for doing our air detection at these speeds. You have to be able to receive a signal, you have to recover the clock, you've got to equalize it, provide reference equalization, and then you need to do an air evaluation of that signal. The real-time scope is naturally great at doing this sort of thing. And it's one of our go-to platforms for this next speed grade that people will be embracing here with both IEEE 802.3 DF as well as the emerging OIF CEI 224 gig specifications, which projects have been started there. We're doing a Keysight Education Forum track on this here on Thursday, so we'd invite people to attend that to learn more about both these instruments and the technology and the measurement science behind the emerging 224 gigabit per second rollout. All right.
Great. Thank you so much, John. Now we're going to walk around the booth here, and I have a real special treat for you. Earlier this week, we did a launch And we have a brand new product in the next solution, industry leading. And actually on top of that, I also have Steve Reinhold, who is sort of YouTube famous, and I like to call my BERT superhero. So do you want to show us your solution you're showcasing here?
Yeah, sure. Thanks. Again, I'm Steve Reinhold. I'm very happy to be here at DesignCon in person, and I'm super excited about our new product introduction. This is the M8050 120 gigabaud BERT. So what we have here, she's zooming in on it, is our BERT pattern generator. We're connecting the outputs to both our DCA sampling scope and our UXR real-time scope. The DCA we're going to use for measuring some parameters. This PG has extremely high signal integrity, so we're going to be showing rise times and intrinsic jitter on the DCA. And we're actually using the UXR as an error detector for the BERT. So the UXR allows clock recovery and equalization and can measure BER. So the BERT software is using the UXR as the error detector in this setup. And so the M8050 allows pathfinding in the 1.6 tera or 224 gigabit per lane arena. It's very flexible, so it has not only extremely high signal integrity, but it allows 7-tap de-emphasis with programmable cursor position. Again, it has really fast rise times, 5 picoseconds. We'll be able to show you that here in a minute. And just a breakthrough product for Keysight with our BERTs. So now I'm going to ask Luis to show you a couple of the features here. What he's going to do here now is run the BERT error ratio test. So again, we're putting the PG signal into the UXR as the error detector. And if he runs it, we have 0 BER shown. And so now if he turns on error injection, we should be able to show we're now injecting errors at a 1e to the minus 4 rate. So you can see that we're not pulling any tricks. Go ahead and turn it back off, Luis. And now we actually saved a couple screenshots. Oh, sorry, we're back down to error-free, of course. We actually saved a couple screenshots we took earlier, so go ahead and flip over to those. So the first one is showing a 120 gigabaud signal with sub 5 picosecond rise times. And then the second one we'll show you is that if we measure intrinsic RJ on that signal, we have less than 100 femtoseconds, which is the spec. We're at 83 femtoseconds right here. So those signal integrity, the signal integrity performance is needed for customers doing this 224 gig or 1.6 terabit pathfinding. So again, I'm super excited to be here with our brand new M8050 BERT, which we're introducing here at DesignCon. Again, enables the pathfinding for 224 gig per lane standards with the world's highest signal integrity. So we're super proud of this new product.
Set it to 11.
Thank you, Steve. That was great.
Okay.
Thanks, Luis.
And thank you, Luis. All right, the next few sets of demos, we're going to go through rapid fire. And our next one's around receiver tests. So here we have Stephen Muller, our solutions engineer.
Thank you. Here at the PCIe Gen 5, Gen 6 receiver test station, we're showcasing our M8040 bit error rate tester, UXR oscilloscope, and our N5991 receiver test software. The M8040 bit error rate tester is the same platform that's being used today for all Gen 5 compliance testing. It's Gold Suite approved. It's a highly integrated platform that's used for both characterization of receivers and the compliance testing itself to understand the true receiver performance. The UXR is used during the calibration process to tune the M8040 outputs to get the exact signal impairments that are needed and specified per the PCIe standard. The N5991 receiver test software automates and guides the user through the calibration and test procedures as required by the PCIe standard. The final calibrated signal is sent through the ISI channel to a receiver where error rate measurements are made and the receiver performance can be evaluated. The M8040 platform is the only Gold Suite approved platform that supports both NRZ and PAM4 signal generation and error detection.
Thank you, Stephen, for doing that super fast. So this was the receiver test demo. We also have the transceiver test demo over here with Rick. So Rick Eads, will you please show us your demo?
Oh, I'd love to. So welcome to the PCI Express Gen 6 demo for transmit test. And so today we're showing that even though the specification for PCI Express 6.0 dropped in January of this year, we're 3 months later, and here we have silicon, real silicon from Synopsys that is operating at 32 gigabaud or 64 gigabits per second. So what we're showing at this show represents tools that customers use for doing validation of silicon, and later there'll be actual systems for PCI Express running at 64 gigabits per second. So here we have an example of our compliance test tool. So this is a prototype tool which shows the ability of the application on the oscilloscope to be able to make all the measurements for PCI Express 6.0. So there are a number of things that are new. One is signal to noise and distortion ratio. One is 48 edge jitter measurements. We have another PAM4 level measurement that we need to make, and we also have new requirements for measuring the signal de-emphasis that's being transmitted by the device. Now what we show on screen here is actually a real live signal. So this is live. It's being generated by the DUT and from Synopsys, and we're showing a 48 edge measurement of the PCI Express 6 compliance pattern for jitter. So there's a 52 UI pattern being generated by the DUT going into the scope. The scope is a 113 gigahertz scope, knocked down to 50 gigahertz, and then you can see each of the edge transitions that are being measured for the PAM4 signal. So what's important to note is that each of the transitions, the level 0 to level 1 transition, level 0 to level 2 transitions, all have different slew rates. And so we want to measure those and then combine those together so that we get a good sense of the overall jitter performance for not just a single edge, but all of the different possible edge transitions in the PAM4 signal. So that represents really our entry into providing customers with a good measurement tool sets for validating silicon on a technology that is really hot off the presses, and we're very early into that market.
Thank you so much, Rick.
Yeah, you're welcome.
Let's switch gears a little bit. We have a DDR5 demo with Randy White. Randy, do you want to show us your demo?
Sure. Yeah, we have a complete DDR5 TX and RX station. On the right, we have a BERT this is a new fixture that's used for DDR5 receiver test. We have a test card inserted into the fixture. We're testing an RCD component. So the BERT's it's already calibrated. It's gonna send out a test pattern while in loop back and then measure the errors. I want to draw your attention up to the top here. The magic that makes this all happen, makes it seem so seamless, is this receiver test application. We've gone through all of the calibration steps. We're calibrating RJ, SJ, ISI, and we have the final stressed I calibration in view there. And that's how we know that we're meeting the spec. So that's for silicon characterization. And on the left here, we have now in-system test. So this is an off-the-shelf DDR5 motherboard. And we have these new probes. These are the most recent, latest high bandwidth probes from Keysight. These are the MX series. The nice thing I like about these probes is they're half the size. So basically you can get twice the number of probe connections on this board. And we're automating some of the new jitter tests for DDR5 with the app.
Thank you, Randy. All right, now we're going to go back into signal integrity. And here we have Mike Resso. I'm going to move Martin out of the way. Mike Sparky Resso is an SI scientist. Do you want to show us your demo? I see a configurable PXI chassis here.
Yeah, I'd be glad to. Thanks, Marlo. So what we're showing today at DesignCon is we have a scalable vector network analyzer based on a Pixie chassis, and you can have anywhere from 2 ports up to 16 ports in this chassis, or a double wide chassis up to 32 ports. What this allows you to do as an electrical engineer is to design servers and internet infrastructure with the ultimate in precision, because we can calibrate this system up to the reference plane up to 57 gigahertz. So what we're looking at here happens to be a mezzanine connector made by a company called Samtech, and this is a very small connector with a very small footprint, and the smaller the devices under test become, the more difficult it is to analyze in different domains. So what we've done here is we have special calibration software, and then after the S parameter data is taken, we can actually do a fast Fourier transform or inverse fast Fourier transform and look at both frequency domain, like insertion loss and return loss, but also in time domain, we can look at the impedance profile, where we see the actual connector under test in the middle and then two transmission lines on either side. And if you look down here, the connector is this backside here connecting these two cards, and the transmission line is on either of these cards here. So one of the main figures of merit for high-speed digital design is called the eye diagram. And what's interesting here is at these data rates, 112 gigabits per second, we actually use what's called 56 gigabaud PAM4. This modulation technique, pulse amplitude modulation, gives us 3 eye diagrams, and so we can measure each of these eyes separately to make sure they're open, so the receiver sees all of the information they need to with the lowest bit errors. So, in summary, we have a hardware system that's the first scalable vector network analyzer running with both physical layer test system software and also a firmware native VNA option TDR that's running in the black here. And so you can really have a choice of how you want to view the data, and the best way really is to do multi-domain analysis. Whether you're a digital guy or a microwave guy, you want to be able to look at both time domain and frequency domain. Thank you very much.
Thank you, Mike. And by the way, I consider you like a DesignCon OG. Like, how does it feel to be back?
It's awesome. You know, it's been a couple years, and it's great to see the old colleagues here, and it's just exciting to see the energy and people get pumped up about what's new and the new technologies. How do we make these measurements? And Keysight has always been kind of the go-to company for sharing our expertise and being able to educate the public. So being part of the team here is really great. So all I can say is teamwork makes the dream work.
I did not tell him to say that. All right, let's go around the corner here. Our next demo is around USB 4 and and DisplayPort 2.0. And here we have Jit Lim, strategic planner, the big cheese, who is going to do a demo and show us his demo here.
Hi there. I'm here. We are testing a USB 4 dock. And on the left, on the screen, we're actually doing a very complex receiver testing, but it's fully automated. So all I got to do is kick back and watch the test run. And let's take a look at what the test results would look like. So this is the test results of this automated test. And all we're looking for is right here, which is 0. We're looking for a BER of 0. So in this entire complex setup, we're looking for a 0, which means that we're doing good. And on the right over here, we're doing the same thing on the transmitter test. In addition to that, we're doing a return loss test with this ENA. But that's not all. Way to the right here, so we actually have a piece of Synopsys USB 4 IP we are testing. So the inputs are going to here, and you see this wonderful eye, a very wide open eye that easily passed the test. But more important than that, what I'd like to show you here is that these results show the correlation between Keysight simulation software and the final product. From the left, before you even turn your silicon, you have to know, does it work? Before you invest anything. And this is simulation result. And at the very end, when you finally have a product that you're measuring on the physical layer, which is that board that you see here, you can see a perfect correlation between simulation in the very beginning to us finally testing the physical product at the very end.
So you talked a little bit about USB 4 testing. Does this also work for DP 2.0?
Yeah, the rates are similar. So the DisplayPort 2.0 rate also runs at 10, 20 gig, and 13.5. So the testing methods are very similar, and they also share the exact same Type-C connector. So very similar methods of testing, but different use cases. One is for data mainly, and one is for display.
Great. And I don't know if you guys know this at home, but Jit's actually wearing some really cool socks. I think it gives him some dancing capabilities. So do you want to...
As I said earlier, testing is automatic. So when I am testing and it's automatic, I need to be dancing. So I brought my dancing socks. So time for the big reveal here. Drum roll, please. Yeah, baby.
Keysight really does care, apparently. So thank you so much, Jit. All right, we're almost at the end here, and the next demo that we have is around FEC and impairment. We have Charles Seifert. Would you want to show us your demo, please?
Thank you, Marlo. This is a 112G electrical lane stressed receiver test where we also measure forward error correction performance by injecting stress into the device under test. The device under test is a OSFP 2x FR4 optical transceiver and a module compliance board. Our Keysight M8048 BERT tester is injecting an impaired signal, a stress signal on lane 1, and the Keysight G800 GigE is injecting FEC scrambled idle traffic together, and these are synchronized by clock and trigger cables, so they're injecting together. The device is being tested, the optical transceiver, as if it was in a real network because it's under link, and we are sending FEC traffic, injecting stress, and we are measuring the effect of the stress on the device by looking at how many FEC code words and how many symbol errors are in code words and doing a distribution. The goal is to have a frame loss ratio of 0 and a prefect bit error ratio of 10 to the minus 4 or better, and to have no FEC uncorrectable code words. So this device would be a pass because we are injecting stress and it's still passing even when the stress has been injected.
Thanks, Charles. All right. Well, last but not least, let's go see our latest in digital design software. So here we have Stephen Slater, our digital bloke from Australia. Want to show us your demo?
G'day, Sheila. Happy to play along this story.
I'm not Sheila. I'm Marlo.
Okay, we have a very cool demo here. It's all about simulation. And as you go from DDR4 into DDR5, you can't just leverage the same design. It's a chance for a new design start. And so what we're showing is how to do a pre-layout design. So inside this block, we have the ability to set up individual, this is via models and transmission line models. You can set them to be parameterized, so we could sweep them. This is a look at what one of the via models would look like, which is kind of very cool, and do an EM extraction of this. And then when we simulate, what we're really trying to get to is something that looks like this. So this is a representation of a Xilinx FPGA evaluation kit, and you can kind of see it here. The main board is represented here. Then we've got a DIMM connector that's represented here, and then we plug into it the DIMM, and the DIMM is represented by this one here. And then these are all of the individual memory devices, and you can see the eye diagrams and the waveforms for each of these locations. So the key thing is, how good can these pre-layout models be at predicting performance? And that's where I'd like to show you this. This is a representation of FPGA. I could analyze this whole section, this is a real layout, analyze it with an EM model, so with SI Pro, you get an eye diagram. But if I do exactly the same thing in pre-layout, so here with this block, you look at the shape of the eye diagram and look, the eye height, there's only a 3 millivolts difference. So it gives you a lot of confidence that I can do a pre-layout design, feel comfortable that I've got the right design constraints, and then go into laying out the board and then verifying. And that's what we have. That's what we're showing today. Thank you, Molly.
Thank you, Stephen. All right, well, there you have it. This is our booth here at DesignCon here in Santa Clara Convention Center. We hope you enjoyed touring the booth. Be sure to tune in tomorrow. We have 7 Keysight Educator Forum technical sessions that we're also live streaming. But before we wrap up, Carmina, any closing thoughts?
Oh, sure. I just wanted to say, folks, we're here to help you. We're here to support you. Whether you have a demo or you need to talk to somebody, just let us know. We're here to help. We have software, hardware, and services solutions for you. And so, Marlo, good job interviewing. That must have been fun. It feels good to be back. I had to buy a new pair of pants. I don't know about you.
Oh, yeah. Wardrobes have changed.
Yeah.
But we do hope to see you at the next event where Keysight can help you accelerate innovation to connect and secure the world. So on behalf of Carmina and myself, thank you for watching and have a great day.
Yeah, have a great day. See you soon.